All right, let's get right into it. If you're serious about a career in the cockpit, what we're about to cover isn't just some textbook theory, it's the fundamental language of the sky. We're talking about atmospheric stability, and trust me, understanding this stuff is absolutely crucial to becoming a professional pilot. I want you to start thinking of the atmosphere less like empty space and more like a vast, invisible ocean. Seriously. It's got currents, it's got eddies, and it has some incredibly powerful vertical movements. Your entire job is to fly through it safely. So, how in the world do you navigate currents you can't even see? Well, to get a handle on all this, meteorologists came up with a pretty brilliant tool. So let's meet the main character of our story today, this little thing called the imaginary parcel of air. Now, to be clear, this is not a real bubble of air you can go out and find. It's a concept. We just imagine a self-contained pocket of air that we can track as we lift it up or push it down. And the really important rule here is that it doesn't mix with the air around it. This lets us predict what an entire column of air might do just by following the behavior of this one little sample. And don't think this is just some tiny concept. As the Royal Canadian Air Force Weather Manual points out, these so-called parcels can represent anything from a small bump of turbulence all the way up to a massive air mass that's big enough to spawn a thunderstorm. It's a really scalable idea. So, this brings us to the million-dollar question for any pilot. If we give this parcel a little nudge upwards, let's say we force it to go over a mountain range, is it going to keep rising all on its own, creating clouds and turbulence? Or is it going to be heavy and dense and just want to sink right back down, giving us that smooth, stable air we all love? That's what we're here to figure out. Okay, so first things first, we need to understand the fixed rules that our little parcel lives by. It doesn't matter what the weather's doing outside, our parcel of air has its own internal, totally predictable physics. Think about it. As any chunk of air rises, it moves into an area where there's lower pressure, right? So there's less stuff squeezing on it. This lets it expand, and that very act of expansion causes it to cool down. It's a basic law of physics. This process is called adiabatic cooling, and the key thing is it happens at a very, very predictable rate. Now, our parcel kind of has two different personalities, which you can see right here. On the left, if the air is dry or unsaturated, it cools at a constant rate we call the dry adiabatic lapse rate, the DALR. Simple enough? But on the right, if that parcel is saturated, meaning it's a cloud, it cools at the saturated adiabatic lapse rate, the SALR. See the difference? The saturated parcel cools slower. And why is that? Well, as water vapor condenses into cloud droplets, it actually releases a tiny bit of heat. We call that latent heat. And that little burst of warmth works against the cooling from expansion. So these two rates, the DALR and the SALR, those are our parcel's fixed internal rules. Okay, so we know the parcel's internal rulebook. Now, let's look at the environment it's actually moving through, the real-world atmosphere on the day of your flight. This is what we call the environmental lapse rate, or ELR. And unlike the fixed, predictable DLR and SALR, the ELR is what's really happening out there. It's the temperature profile you'd get if you sent up a weather balloon right now. It is constantly changing, every single day, every single hour. And this ELR can have a few different flavors, you could say. You might have a steep lapse rate, where the temperature just plummets as you climb. That hints at instability. Or you could have a shallow one, which suggests stability. You can even have an isothermal layer, where the temperature doesn't change at all. Or an inversion, where, get this, it actually gets warmer as you go up. Those are signs of extremely stable air. So here we are at the most important point of this whole thing. Atmospheric stability is nothing more than a simple comparison. That's it. We're comparing the temperature of our theoretical parcel, which is cooling at its fixed rate, with the temperature of the actual environment around it. The relationship between those two, that determines everything. All right, time for the showdown. Let's put all these concepts together and see what this comparison actually looks and feels like when you're sitting on the flight deck. So let's ask our big question one more time. We give our parcel a push upwards. Is it now warmer and more buoyant than the air around it, causing it to accelerate upwards like a hot air balloon? Or is it colder and heavier, causing it to sink right back down like a rock in a pond? This table really lays it all out. First row, absolute instability. This is when the environment is cooling off so fast it's even faster than our dry parcel. The rule is ELR is steeper than the DALR. What does that feel like? Strong updrafts, serious turbulence, and maybe even thunderstorms. Now row 2. Absolute stability. Here, the environment is cooling off super slowly, even slower than a saturated cloud. The rule? ELR is shallower than the SALR. You're going to get smooth air for sure, but also probably haze, fog, and just poor visibility. And finally, the tricky one, conditional instability. This is when the ELR is sandwiched right between the two parcel rates. This air is stable if it's dry, but if you lift it high enough to form a cloud, then it becomes unstable. So when you look out the window and you see a sky filled with those big, towering cumulus clouds, you're not just looking at water vapor. You are seeing a giant visual confirmation of an unstable atmosphere in action. Understanding these rules is what lets you look at a weather chart and predict with real confidence what kind of day you're going to have. I want to leave you with this really powerful thought from an old flight instructor. He said, "Weather moves horizontally, we move vertically. If you don't understand how they interact, the weather moves you into the ground." I mean, that just perfectly captures why this isn't just an academic exercise. Wind and fronts move across the map, but we fly up and down through that weather. And the interaction between your vertical path and the atmosphere's vertical stability, well, it can be a matter of life and death.
At the end of the day, understanding atmospheric stability isn't really about giving your passengers a smooth ride. Though, that's a nice bonus. It's about maintaining command of your aircraft. It's about knowing what the air is going to do before it does it. And that is the mark of a true professional pilot.